gosh, God, that was the finale. What a mistake. Little teaser there. You're thinking, what was it? Well, thank you very much. Thank you very much for the invitation. And I'm sorry I've not been the most sociable today. I got off the plane and one of my ears popped and the other one hasn't. It's incredibly disorientating. So I apologise for my poor form. Right. I'm going to talk about the resolution limits of ghost imaging. And at one level, oh, I need to press the button. Yeah. I'm sure you heard the first half of the sentence anyway. I'm going to talk about the resolution limits of ghost imaging. And it's partly triggered because I just get a little narked when I read people making claims about, you know, oh, we can see sub-micron resolution at a range of 300 kilometers through 20 meters of Earth. And I can understand why that's exciting. It just might not be true. And so first of all, I'm going to go through a system and actually show you why, in terms of resolution, I don't think ghost imaging is magical, and actually I don't think ghost imaging can beat the classical limit. And then I've got some pictures at the end which do beat. In fact, you've just seen one of them. Okay, so you'll have to wait. So, of course, I'd particularly like to thank Paul, who was also an old friend of Bristol. He is fantastic, and he's with me at the moment as a Marie Curie fellow, and he just does experiments properly, and with inspiration as well. And I didn't mean that in any bad way. He's one of the people in life that does things properly, and when he comes to you with results, you know that the results are right. So before going any further, I just want to be clear about what I mean by ghost imaging. I mean ghost imaging as put forward in those fantastic papers of the 1990s by Yang Washi. And so I mean ghost imaging where I use a parametric down conversion source, and one of the beams, is that just me or is that sort of shaking from side to side? Interesting. One of the beams goes off through the object, the other beam goes off to some kind of imaging detector, which traditionally was a scanning single point detector. And I just want to point something else out here which is really important. This detector here has no spatial resolution. Indeed, it must not have any spatial resolution. It is drawn as a big bucket deliberately because it has to be big enough to collect any photon wherever it goes through the image. And that's a bit of a problem, because it means I need a detector there which has a large, in classical optics terms, étendue. It cannot be a 5 micron diameter detector. Full stop. Okay? It cannot be a single mode fiber. It must be a large detector with, roughly speaking, as many capable of detecting as many spatial modes as there are pixels in the image that you're ultimately hoping to get. Now, clearly you can do it with a smaller detector than that, but just don't expect to be able to do it efficiently. This second detector here, obviously you do want to be small because you want to scan it around and you want to measure spatial position. So the size of those two buckets is deliberately chosen. Now, and that's the gig. And obviously, and I'm going to be very naughty here, I've got a big pump beam here. In fact, somebody said earlier today, didn't they, that if you're going to do imaging with this kind of light, you better make sure it's multispatial modal to begin with. And that's a very good saying. So this is a big pump beam and a small crystal, thin crystal. It's producing many, many, many spatial modes, probably in a millimeter thick, 3 millimeter pump beam. It's probably going to be producing something like 2,500 spatial modes, maybe more. And you can sort of think that the photons are going to be born together, and they're going to be born together somewhere within the diameter of the pump beam. You just don't know where. That's a random process. And then you're going to match the size of the pump beam to the size of the object. You're going to match the size of the pump beam to the size of your imaging detector, and that's all great. All of these things are sort of fairly obvious when I say them now, but the first time you set up one of these experiments, you spend months wondering why it doesn't work, and then that's the answer. But that's inherently inefficient, because most of the time my little bucket at the bottom there is in the wrong place. In fact, the maximum efficiency of that system is going to be the reciprocal of the number of pixels in the image. Oh dear, this is not setting off very well. So how can it be more efficient? Well, I'm going to replace that little silly scanning detector at the bottom, of course, with a camera. Why have a scanning detector when you can buy a camera? Now, I can buy a Canon 5D Mark III, probably the best scientific CMOS you can buy for a fraction of the price of a scientific CMOS camera. And it will have a readout noise, probably sort of 2-3 electrons per pixel. It will have a quantum efficiency of 80%. So that tells you per pixel, you're not really going to be able to see a single photon, unfortunately. You're going to be down at the 2-3 photon level, maybe. I could use an EMC-CD. I can get down to that. If I put an EMC-CD camera in a dark room, in a dark box, in another dark box, in a sock, and turn all the lights off and fill up the cap underneath the door, so it's completely dark, and I go, give me a frame, I'll probably find that most of the frame's black, and there'll be about 1 in every 200 pixels will have a false positive. That's the sort of the dark count rate, if you want to compare it to sort of other things. And in that sense, it's nowhere near as good as a superconducting detector, which if you compared the maximum count rate to the dark count rate, you would maybe have 10 to the 6 or something, I don't know, 10 to the 8 maybe, in terms of absolute contrast. Here, for single photon detection, your EMC-CD has got a maximum contrast of about 200 to 1, although it does have 250,000 pixels, so it's not bad. What about the other kind of camera that I might use? An intensifier on a CCD. If I keep the gate time short, 10 nanoseconds, I can trigger the gate, read out the CCD, and if I'm lucky, get nothing. So actually, although the quantum efficiency is much lower, let's say 20% rather than 80%, the false positive rate, when used on a short time scale of a few nanoseconds, is very, very low. And so you can actually go, nothing, oh, there's the photon. You can't do that with the EMC-CD camera. And so it is an intensified camera that I stick there. The bad news is, and so you can see what is going to happen now. You just go, whenever this detector goes click, it means a photon got through this object, and I'm going to measure the position of that photon by actually taking a picture over here. So I'm sure this camera takes images of photons that have never interacted with the object, hence why it's called ghost imaging. But do not be fooled. There's a whole pile of photons up here that have interacted with the object. So it is not demolition-free measurement or that kind of thing. It is just, in a sense, a heralded detection system. And all I have to do now is get the signal from here to the camera there. Clearly I've got to do a little bit of overtaking the speed of light in order to do that. But worse than that, because this camera, even when you fire the intensifier, is going to take 20, 30 nanoseconds to actually fire the intensifier, for reasons I never really understood, but that's because I don't design intensifiers. So what you do is you put a delay line in the system, which means that this photon can be detected, this photon's still bouncing around, and yet you can still pick it up on said camera. And what does it look like? It looks something like that. I won't bother, but you can see this is the delay line here. The important thing is it's an image preserving delay line. I did think of buying a very long endoscope instead, but as that's about 40 feet, it would have to be, thank God you don't buy endoscopes which are 40 feet long. Where would you put them? Actually, I thought they used to make them, believe it or not, for inspecting between double hulls on ships. Because you want to look down the double hull. People used to make really, really, really long endoscopes. Anyway, such is life. So, here we go, and I know some of you have probably seen this image before. This is an image being acquired photon by photon. None of these photons ever having interacted with the object. What kind of rate can you do? Well, the intensifier will trigger 50,000, 200,000 times a second. What you generally do is trigger it for a second or so, then read a frame out, and you're going to find a few thousand photons in that frame. And I could go on now and talk about image estimation based on shot noise limited data. I love those kind of problems, and I've learned all about image regularization and log likelihoods and things, but I'm not going to do that. So, next question. Clearly it uses a parametric down conversion source in order to work. Is it quantum? Of course, those of you that follow the literature since the 1990s will have known that people argue left, right and centre about whether it's quantum or not. It uses a parametric down conversion source. It uses the fact that the photons are position correlated. My handkerchief is position correlated. It's here, or it's not there, and it's there. I mean, there's nothing particularly spooky about position correlation. What's spooky is that I can choose to measure either position correlation or momentum correlation. That's the basis of the EPR paradox. And so what does that look like in the context of a quantum imaging system? So let's be a little bit more careful about how one sets it up. In this setup, the plane of the crystal is imaged to the plane of the object. Two photons that find themselves position correlated here are position correlated here. And therefore that's why I can put the camera here instead of there, and I can take a picture based on the position correlation. Alternatively, I can put both object and camera in the far field of the crystal. Now, the position correlation here is irrelevant. What is relevant is the momentum anti-correlation. So when this photon goes a little bit up here, the other one goes down here, and hence my image is inverted. Not in a contrast sense of the word, in a geometrical sense of the word. Interesting question to think about how you would choose to produce a inverted contrast image. Think about that. Does it have something to do with symmetric states and anti-symmetric states? Anyway, let us leave it for a moment. You'll be glad to know you can do those experiments. You can change the lens system from being an imaging system to a far field system by using spatial light modulators or deformable mirrors or whatever. So you can actually flick backwards and forwards between these two things, and what you discover, actually what you discover, I hope you can see it here, is that you can switch between the upside down image and the upright image. And that is a manifestation, sort of, we'll forget about timing loopholes and all those kind of things, but that's a manifestation of EPR. From a practical point of view, there is another alternative to wanting an upside down image, which is you take it into Photoshop and flip it upside down, or you pick up the screen and rotate it round. So from a practical point of view, the fact that I can get an upright or an inverted image is not perhaps the most exciting thing I can do. Can it do something different? Well, yes it can. Of course, I do not need to run my down conversion source at degenerate wavelengths. I can run it at non-degenerate wavelengths. In this case, I am probing the object in the infrared and recording the image in visible. That's great because that camera there, that intensified CCD, doesn't work in the infrared, nor is it going to anytime soon, because the infrared photocathode on the intensifier would be so frigging noisy, you would never see a single photon. Well, you see a single photon, you just see lots of noise with it as well. So you're doing something there. This detector, fantastic, but remember, it's actually not trivial, because the detector needs to have an étendue, or a diameter, which is quite large. In this case, it's an Ingas SPAD from Alberto group. I think it was 25 microns. So it's bigger than a superconducting nanowire. And if you're going to replace that detector with something else, it's going to need to still be big. I guess the question then, though, I could just have bought an infrared camera, and that's a difficult argument to beat. But maybe one can go further. John and I were talking today. How far can I do parametric down conversion at dissimilar wavelengths? Can I get to terahertz? Can I go beyond terahertz? If I could do a split here between a visible photon and a terahertz photon, maybe I'm in a regime where being able to use correlation to map those terahertz photons into visible detection events, that would give me a very, very low dose terahertz imaging system. Very low dose, I mean single photons of terahertz radiation. I think that would be exciting. Here's some real images of it's actually gold etchings on a silicon wafer. In transmission, I'm recording those transmitted images with blue photons, even though obviously the blue photons didn't go through the silicon, but the infrared ones did, just as a thing. Now, all of that I've spoken about before. I'm just going to, it's a bit of a tutorial session now. How do you understand a ghost imaging system when trying to predict how it's going to behave? That was all taken care of in the original papers by Shi et al. By Klitschko's, I believe, Klitschko's understanding. This is what I've spoken about so far. I've got image plane crystal to the object to the camera. How can I predict what image the camera is going to see? What I do is I replace this detector with a light source, shine light from the detector back towards the source, and I replace this source with a mirror. I'm going to make that change. Nothing else changes, okay? Now this is not completely bonkers. People, if I really want to be pretentious, which I do because I'm a physicist, I will talk about time reversal. I'm going to time reverse this photon detection event and project it back in time. And then I'm going to let it run forward in time again. Retrodiction. Now these are hugely powerful techniques. And then you see I've actually just built an imaging system where the source, the object, is imaged onto the mirror, and the mirror is imaged onto the camera. And that would predict essentially the same image as I'm going to pick. So in a sense, this system here, this classical system, the simplest imaging system that mankind has ever made, is a classical simulator of the quantum system. Now, of course, this was simultaneous detection events, this was sequential. It is in no way an explanation of quantum mechanics or anything. It's just a predictive tool in trying to guess what's going to happen when I start introducing pinholes or phase filters or all things that you'd think might, what happens if I turn one of these beams into orbital angular momentum? Why would I do that? Well, because I would, wouldn't I? How is it going to behave? What's it going to do? Well, actually, this is the predictor. This allows you to predict what's going to happen. If only I knew how to do quantum computing with this, maybe I could actually just do it with a classical system. Obviously, that's not true either. But one wonders. So there's my upside down version as well. That works perfectly. Now, this mirror is in the Fourier plane. And we're going to think about, what do I do in the Fourier plane? I can put a spatial filter in the Fourier plane. I can do low-pass filtering of the image by reducing the size of this mirror. What does that mean? Like reducing the size of the nonlinear crystal? Well, I don't even need to do that. I just need to reduce the size of the pump beam. It's the pump beam. The diameter of the pump beam is effectively setting the size of this mirror in the classical simulator. So if I want to know how is my quantum imaging system going to change its behavior when I reduce the size of the pump beam, I just have to think, how does my classical system behave when I reduce the size of the mirror? It's the same thing. So we better just check that these things are true, and there's actually, these are experimental results. I don't quite know why these are so dark, honestly, they're really there. Where I've got on the one hand the quantum result at the top, on the other hand I've got the classical result at the bottom. And these systems are unbelievably the same. Because actually, in the real world, in the lab, this bucket detector is a multimode fiber to which I've connected a detector.
All I have to do is unscrew my detector and screw in an LED, and I've turned my detector into a multi-mode source. This crystal here has a front face on it which is fairly flat. If I just stop pumping it with the laser, it becomes a mirror. Albeit not a very good mirror, it only reflects 4% of the light, but that's okay because my LED is bloody bright. And so actually all I have to do to switch between the quantum system and the classical simulator is unscrew the detector and screw in an LED. And so these are the same images for a reason. Actually, you can spot the difference between G1 and G2 because the quantum image isn't speckly, whereas the one produced by the LED is because of the spatial coherence in the LED. So there's actually quite subtlety in there. Anyway, what I really want to talk about is setting the resolution, of course, because that's what the title of the talk was called. And I think I've tried to suggest to you that one of the key things in setting the resolution is the size of this mirror here. Actually, if you just think about it generally, if I replaced both of these things with cameras, and I could see the position correlations, an interesting question to ask yourself is what's the strength of the position correlation? Because ultimately it's the strength of the position correlation that's going to give you the resolution of this imaging system. Clearly, I think it's clear, although you'd be surprised, if I make this a really shit lens, so this is a crap image, the position correlation is not very good. Quantum mechanics is not that magic. You only have a good position correlation if you measure position with a high fidelity. If you scramble it all up, it's no longer particularly well. Because if you put a multi-mode fiber in the way, it's not going to be position correlated anymore. Similarly, there's a fundamental underpinning correlation strength, which guess what? Depends upon the size of the pump beam. In fact, you know that that's the case. It turns out to be this. Look at the math. Actually, in the far field, where I'm actually imaging the momentum correlation, what is it that sets the strength of that correlation? It's actually the diffraction limit of the pump. It's the transverse momentum uncertainty in the pump beam, which tells you the momentum correlation in. And the great thing is, you think about it, the pump beam is sort of effectively always changing directions slightly in accordance with the divergence. It's a perfectly collimated beam, which is changing direction slightly because the beam is diverging, and that means that these two photons at the end are moving around a little bit with respect to each other. So this is the key thing, and then you turn that into position by knowing the focal length of the lens. But this is the important thing, that's the beam waist of the pump. And my hypothesis is, no matter what you do, pal, you're not going to beat that resolution. So let's see whether that's true. So in order to do that, it's very difficult to do a fair test. Well, it's not very difficult, but you always worry, oh, is it in focus? Was the lens okay? Was it aberrated? So this is the system we've spoken about so far. I've got my photons going off to my object. Well, my camera was here, my detector was here. And what I've done now is just added on a re-imaging arm. So I can put the camera in here, or I can put the camera there. Makes no difference. It's a unity magnification delay arm. But actually that's really good now, because now I can put the object there. That's a ghost imaging system. And I'm going to get an object here, works fine. Or I can move it down to here, because that's also in an imaging plane. And so now I can go backwards and forwards between doing ghost imaging and just classical imaging with a down-converted source. Now, what do I expect to happen? Well, if I go into the Klitschko picture, I've got my light source here. It comes along, it illuminates the object. It then goes onto a spatial filter, and then I image that. And if I shut down this spatial filter, I'm going to get a blurry image here. On the other hand, if I put the object here, it's just fine. Because all I'm really doing now is spatially filtering the light source before the light source interacts with the object. Now, there are subtle differences depending whether I illuminate an object with a spatially coherent source or an incoherent source, but they are subtle differences. So let's just do that. And I do that, and ghost imaging works just fine. And it's pretty much the same as ghost. It's pretty much the same as ghost as normal imaging. And now I have to make the pump beam smaller. And what do I find? Well, there it's fine, but when I go to there, this image gets blurred. That's what I might think. Let's see whether that is actually what happens. Again, I apologise for the contrast here. You just have to believe me, okay? This is object and camera in the same arm. It's one of these really test target things, As I reduce the pump beam size, nothing changes. On the other hand, object and camera in different arms, as I reduce the pump beam size, oh dear, the resolution's degraded. So everything we think we know about ghost imaging is true. And there's interesting things. I think the wavelength transformation is interesting. I think the fact that you're heralding your photon arrival means you basically take noise-free images. There are no dark photons in my system because essentially it's a conditional detection. So all of that low light imaging, yep. Magically enhanced resolution? No. This relates to a Popper, the philosopher Popper. Thought experiments, and physicists love quoting philosophers because it makes us seem clever. I don't really know what Popper thought. I think I know what Popper thought. And he asked a very interesting question. Because we know what this is. This is a down conversion crystal. We've got photons going off to the left and to the right. We know they're position correlated. We know they're momentum anti-correlated. Simple question, what happens when I put a slit in one arm? Well, when I put a slit in this arm, you know what's going to happen. The light here is going to diffract through it. That's what light does. These photons are correlated, though. What do those photons do? Because they're magically entangled. Clearly, they're going to do something, surely. And so the question is, well, first of all, what do? It's Friday afternoon, it's late, so I won't actually ask for a showing of hands in case it's embarrassing. So his thought was, well, if these photons are entangled, then surely the photons on the left have to do something. But if the photons on the left do something, I've got faster than light signaling. Because all I have to do is rip this little slit in and out, and at Alpha Centauri, I can watch the diffraction pattern. And that would not be good. So let's just do that as an experiment, shall we? Shall we see whether it matters which side you put the slits on? We can sort of do it with the same system as we had before. I can put the slits here, I can put the slits there. Interestingly, you know how you have to illuminate slits with in order to see a diffraction pattern, you have to illuminate the double slits with a spatially coherent source. What does that mean in this sense? Because clearly this is not spatially, I've just told you it's not spatially coherent. It's multimodal. What you have to do, you have to make this detector small. You have to put a pinhole in here. Of course you do, because if it was the light source, you would change the multi-mode fibre to single mode fibre and illuminate the slits that way. So that's all I have to do now is change the fibre. So I take the multi-mode fibre out, put in a single mode fibre. And when you do that, you find that you can record a ghost diffraction pattern. Again, she did all of that. Double slits up here, small buckets, because I want to illuminate in inverted commas. I want to detect a single spatial mode, so the image becomes very dark. Coincidence detection down here. Hey presto, you've got some fringes. Fantastic. Let me make the pump beam smaller. Well, if the slits are on that side, everything's fine, because I'm still just spatially filtered the light source, who cares? But I put the slits back there, the diffraction pattern here is restricted. It didn't flip out. Because what I'm seeing here, let's not forget, is a subset of all the photons that were ever there. That's what coincidence detection means. You're post-selecting on the entire population. And interestingly, just look, this thing here is an image plane of the crystal. So if I didn't do anything, I'd just have an image of the pump beam here. and essentially I apply a pattern to the extent of the pump beam. That's what conditional detection means. And so if I make the pump beam smaller, the field of view here gets smaller. And so in that sense, and different papers in the past have gone, ghost diffraction does work or ghost diffraction doesn't work. The answer is it works, but just not particularly well. So that is the thing. This is the ghost diffraction. What we're doing here is making the slits smaller and smaller and smaller. When we do normal diffraction, you make the slits smaller, you see more and more diffraction orders. When you do ghost diffraction, you make the slits smaller, the number of diffraction orders you get is limited by the pump beam. So that is, in the words of Ben Goldacre, in response to the Popper's thought experiment, it turns out to be a bit more complicated than that. So is probably where we're sitting. Now, I'm not going to bother. This does come back here on this thing about, so where can you play around with apertures and see an image that, you know, if I make the pump beam smaller, my resolution goes down. If I make I didn't show you the results, but I have them. If I make the aperture of this lens smaller to worsen the diffraction limit, resolution goes down. If I make the aperture of this lens smaller, resolution goes down. Where can I put anything without affecting the resolution? I can put it in front of the bucket detector. Because you knew that, because I can put a mask in front of my light source, take a picture of the room, and I still get the same resolution. I can play around with the illumination. I can play around with the bucket detector. If I put an aperture in here, the image gets darker, but it doesn't change in quality. Now, having said all of that, it's maybe the wavelength transformation is quite good. How can I use quantum to give me a resolution enhancement? That's where I started off. What's the resolution of ghost imaging? I'm now going to lose the word ghost and just replace it with the word quantum. Although we can argue whether it's entanglement or correlation, you're right. I'll take out the word quantum and put correlated imaging. So here's a box. On the left-hand side, there's a UV laser with some air extraction pumping a BBO crystal, producing 2,500 modes of spatially correlated light. On the right-hand side, there's an object. There's an aperture, because I want to be able to control the diffraction limit, and there's a camera. So it's the simplest imaging system I could possibly imagine. Good old Hermes, genius this guy is. Again, someone else who actually does experiments properly and well, as you can see from his box, where he has done everything. My down-converted photons are re-imaged onto the object. Both photons go through the object. Both signal and either photons go through the object. This is not separated signal and either beams. And therefore, when I image over here, what do I expect to see on my camera? If my camera has very small pixels, such that the pixels are smaller than the spatial correlation strength. So both of those photons were position correlated, but they do not appear in the same pixel because the pixel's smaller than the correlation length. So they appear side by side. It's like Noah's Ark. The photons arrived 2 by 2 because that's what they do. And then I've got a choice. I can sum all of the photons together and I can get an image. And that image will be classical in every respect. Or I look at every photon pair and go, no, I'm going to take the bisector. I'm going to take the average position of those two identical photons. And then I've had 2 bites at the cherry with the one-armed bandit. And so maybe I see a resolution improvement, we can now argue. I'm going to say root 2. If I had 3 photons, maybe I'd get root 3 or root 4 or whatever. And so that's it. That's it. And you look at these, so you're running the camera photon sparse, so most of the pixels are black. So you're running it fast, you're running it short shutter speed, you're turning your light source down. And so actually what you see on the camera chip are pairs of photons, plus the dark counts. Bit of a pain, but And then you start running all kinds of pattern matching things to go, oh yes, those two are real photons, those two aren't real photons. You try as hard as you can to be smart about the strength of the signals, and you really try and identify the photon pairs. And it does one thing. One is, first of all, you get rid of the dark noise, so you're interested, you've got high contrast, and then you go over it. So let's have this is the competition part now. You have to choose which image do you think is best, the right-hand image or the left-hand image, not aided by the most fantastic data projector in the world. Okay, can I persuade you that I think, it's just, one is the bisectors and the other is the sum. You get the idea, okay? So that bulb filament actually is sharper, higher contrast, because we looked at the photon bisectors, not the photon sum. This is some paper fibre. Again, I hope I can persuade you. This is a flywheel. If you look around here in particular, I hope I can persuade you. And ditto, I won't play in this competition anymore. Sort of works. Do a slanty edge MTF test, and that's where we are. I would have hoped that we were going to get a resolution enhancement of root 2. We see slightly less than half of that. Why is that? It's because, however clever we try to be with our pair detection bisector, blah, 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 every now and again we pick a photon with a dark noise and bisect those, and rather than making the image better, that makes it worse. So you're trading data rate against that. So I think it's I'm quite excited. Okay, and that is the end. So there we go.
For a couple of quick questions.
Thank you very much for the talk. On that last point, so you mentioned how you could maybe do it with like 3 photos or 4 photos to take, I don't know, the centroid or something. What do you think would win out of? So say you go to 3 photons, you've got to identify the 3 photons, and you could make an error in that. That's harder than identifying 2, right? So what do you think you get an improvement, or do you think it would just get steadily worse?
Technology-wise, I think it would just get steadily worse. But actually, interestingly, I mean, it's not rocket science. You can sit down and you write a numerical model quicker than you can do the experiment, quite frankly, to do this. But the exciting thing about a numerical model, I can program it to have different levels of dark noise. And so I go, if my camera was twice as good as it actually is, what would happen? If my camera was 10 times better, if my camera, it turns out, instead of having one dark count per 200, it had one dark count per 2,000 pixels. This whole thing, then you reach your root 2. And actually you get your root 2 quicker. And it turns out the frame rate improves, everything about it. And then you go, well, there's no such thing as a free lunch. And you go, I'll tell you what, I will accept that the quantum efficiency is going to fall from 90% to 70%. What happens then? Turns out still the same. So as I keep on saying to Andor and Raptor and everybody else, I would buy a camera from you, even if the quantum efficiency was 70%, not 90%, providing you get the dark count down. And if you get the dark count down, that's more useful to me for this application, and I suspect many quantum applications actually. It's not the quantum efficiency that stuffs you, it's the false positives that stuff you. And so that's an interesting discussion to have with them. And often you think it's obvious that that must be true, but it turns out the way EMCCs work, you can definitely get lower quantum efficiency. That's not hard. Whether you then get any other performance improvements other than cost is not quite so straightforward.
Okay.
You might have mentioned this, and I just keep trying to understand this. So, in the multi-wavelength one, we have 2 different wavelengths, where the ultimate limit is going to be the diffraction limit, which is a function of wavelength.
Yeah.
Which wavelength is it?
Which wavelength would you like it to be?
Whichever one is the best resolution.
Yeah, so unfortunately it turns out not to be.
Okay.
So unfortunately you get the resolution limit dictated by the infrared, not by the blue. So you end up taking visible images with infrared resolution. But you do get the ability to detect single photons. It's not a complete washout. But yeah, I got very excited for a day.
Maybe one final question. Was there? No. That won't be an easy question. There has to be an easy question.
I enjoyed your analogy with the light source and the mirror instead.
They're not my analogy, sadly, Klitschko's, but fine. Yeah.
If you were to apply the same thing to the final experiment there, is it, I'm aware of a microscopy technique called super ramp, where you like image with a directed beam, you structure your illumination beam, and then you get an improvement over
I think the classical analogy would be a double passed optical system, where you pass the light through, image it, and then re-image it, and then pass it back through it. Miraculously, somehow, get your mirror such that you pass it straight back again in a way that was not diffraction limited. Okay, there's clearly a number of problems there. I think it's a double. I think the analogy in that sense would be the double pass, rather than the structured light. But I'm happy to not be correct.
Okay, I'm going to thank the speakers again. A great talk.